Hello everyone, my name is Altuğ Kaya, and today I'm going to present our reading assignment of the authors Thesalias and Ephremides. This is the agenda that we are going to follow today. In the next few slides, we will focus on the problem statements and constraints. We consider a queuing network model with interdependent service components. Considered queuing network has arbitrary topology containing multiple servers. In addition, servers cannot provide service simultaneously. Our main motivation is studying the resource allocation problem in multi-hop radio networks. In addition, we are interested in scheduled link activation schemes rather than random access methods. We wish to find control policies under which the system is stable for given arrival and service rates. Let's define what the stability is. We consider the system to be stable if the queues do not tend to increase without bound. In the paper, dynamic link activation scheduling are considered, where the activated links are selected based on the queue lengths at all network nodes. Paper claims the maximum throughput policy for the constrained queuing model provides a link activation method that stabilizes the network for all arrival rates for which it is stabilizable. Let's describe the queuing model we are interested in. The constraint network consisting of L nodes and N links or servers. The word links and servers are used interchangeably throughout the presentation. Each link corresponds to a server that serves customers residing at the origin node of the link, stated as QFI. After servers, the customers are directed to the destination node of the link, represented by H of I. A customer may enter the network at any node. A customer's destination is a subset of the network nodes. As long as the customer reaches any of these nodes, it leaves the system. There are J customer classes, which are distinguished by the destinations of the customers, namely V sub J. At each node L, customers of all classes are queued, except of those classes J where L is an element of V sub J. Any customer of this class leaves the system. We consider slotted time. At each slot T, certain links originating from node L provide service. Those are the activated links at slot T. Let's define what the routing is. Customers are not committed to specific outgoing links of a node L by the time they reach L. But at the beginning of each slot, a decision is taken which customers of which classes are allocated at which links. However, there are constraints on the activation of the links, because certain servers cannot provide service at the same time. This problem is handled by the definition of activation set. Activation set is a set of servers which can be activated in the same slot. Let's further define what scheduling is. At the beginning of each slot, an activation set of links is selected that provides service during the slot. The servers are synchronized to start service at the beginning of a time slot. The state of the system evolves according to the following equation. If A's and M's are IID for all servers, classes, and nodes, and if all processes are independent among themselves, and if the second moments of the arrival processes are finite, X of t becomes a Markov chain. As we mentioned earlier, the system is stable if the queue length process reaches a steady state and does not blow to infinity. When a Markov chain X is irreducible, the stability of the system is equivalent to the ergodicity of the X. As we see in the class, irreducibility plus aperiodicity yields ergodicity. It is often easy to verify the irreducibility and aperiodicity of a Markov chain, but in general, it is difficult to directly verify whether a Markov chain is positive recurrent from the definitions earlier in the class. There is a convenient test called Foster-Lyapunov test for positive recurrence check. It says expected drift should be negative for the positive recurrence to be existed. Let's move on to maximum throughput consideration. Systems should be stable for a wide range of arrival rates. We quantified the performance of an activation policy by a stability region. Here are some definitions. The stability region C sub pi of policy pi is a set of multi-class arrival rates vectors for which the system is stable. A policy pi sub 1 dominates another policy pi sub 2, If the stability region of pi sub 2 is a subset of stability region pi sub 1. In addition, the system is stable under pi sub 1 whenever it is stable under pi sub 2. The stability region of the system is the union of all stationary activation policies. The union of all stability regions where their policies are all stationary activation policies. The policy supports the stability region of the system is called maximum throughput policy. One of the main results of this paper is the existence of such an optimal policy. Let's state the maximum throughput policy. Let's assume the policy pi sub 0 achieves maximum throughput. The activation policy is a collection of activation rules. Activation rule decides which server I is activated in slot T and which customer class it serves. The activation rule at each slot is selected in 3 stages. Stage 1. For each server I, a weight D sub I of T is selected. In other words, pi sub 0 tends for each class to equalize the queue lengths of the same class in different network nodes, giving priority to the servers and classes for which this difference is large. Stage 2. A maximum weighted activation vector, C hat, is selected from the constraint set S. However, stage 2 is highly disadvantageous because number of possible activation vectors is larger than the number of servers. Therefore, the solution of the optimization problem is quite hard. In certain cases, the constraints in set S can be put into a specific structure to be utilized in the solution. Let's skip this for a moment. So far, the algorithm selected the candidate servers and cascaded the customers classes for each candidate servers. However, what happens if multiple servers that serve the same nodes are candidates? Then stage 3 comes into play. The activation rule decides the server with the greatest queue length for the candidate customer class, which is decided at stage 1. Here the optimality result comes. The theorem below shows the existence of the maximum throughput policy pi sub 0. Let's define a stability region C prime, where C prime is a subset of C, where C is a subset of C prime bar, and C is the stability region of the system, and C prime bar is the closure of the defined stability region. C prime bar minus C is a subset of C prime bar minus C prime. Thus, C prime bar minus C prime is the boundary of C prime, which is a surface, and it has no interior. In the space where multi-commodity arrival rate vector A lies. Thus, we determined C within a surface in the space where A lies, therefore provides complete characterization of the stability region. Hence, if we can show that C sub pi sub 0 differs from C at most by a surface, optimality of the policy pi sub 0 is achieved. The following 2 lemmas will provide this. Under policy pi sub 0, the system is stable for every A is an element of C prime. In other words, C prime is a subset of C sub pi sub 0. The proof of this lemma is very similar to the proof of max weight scheduling we have done in the class. Another lemma is, if A is an element of C prime bar complement, then the system is unstable for any policy in the class of all stationary activation policies. The proof of this lemma uses the following idea. If the average number of incoming customers are larger than the average customer of outgoing customers, then the Markov chain of the queue lengths cannot be positive recurrent. We have also seen this in the birth death chains in the class. Finally, it's time to give some examples of the applications of the paper. In databases where concurrent processing of several transactions is possible, a control mechanism is needed to prevent conflicting transactions from being executed simultaneously. The constraint queuing model that is constraint provides a model for concurrent processing in databases. Furthermore, the maximum throughput policy PySub0 that we have specified earlier provides a concurrency control mechanism that achieves maximum throughput. The generalized multi-server queue has been proposed as a model for certain parallel processing systems. Because in a multi-server queue system, customers would like to engage a random number of servers for the service. Under the assumption of POSON arrivals and constant service times, the policy PySub0 stabilizes the system as well. This is the reference. Thank you for listening.